Good morning. Now, this is the next session of our chapter that is in your syllabus. It is given by the title Design of IAR Filters from Analog Filters. Uh, Combined to that, there is also a heading called Approximation of Derivatives. Okay, so that is the class 5 Design of IR Filters from Analog Filters, of which we are going to learn about Approximation of Derivatives technique. Okay, briefly, I would say that Mm, this digital filters, actually the first filters that were developed were analog filters, and later these analog filters, the design was modified to obtain digital filters. That is, analog filters were converted using suitable transformations to digital filters. That is how an analog filter is transformed or converted to a digital filter, means that the transfer function of analog filter is converted to an equivalent transfer function of a digital filter. So for that we make use of various transformations, that is, so many techniques are used or methods are used, and some of those methods are approximation of derivatives technique, bilinear transformation technique, impulse invariance technique. So all these techniques are used to convert an analog filter to digital filter. That I mean, to convert the transfer function of an analog filter to the transfer function of an equivalent digital filter. So you are allowed to study all these techniques in your syllabus. So for today we will start with the approximation of derivatives technique. Okay, now this is what I have said now. Traditionally, synthesis of IAR filter, full form is infinite impulse response, low pass digital filter, is accomplished by transforming an analog filter to its digital equivalent, and many transformations are used, as I said now. Then another brief history, that is, usually IR filters are directly related to analog filters. Analog filters are always defined in continuous time. Okay, that is, whereas digital filters are always described in discrete time. So conversion of an analog filter to digital filter means that at mapping or transformation of transfer function, that is HS, in continuous time, that is that of a analog filter, to a transfer function HZ of digital filter, that is in discrete time. Okay, that preserves many properties. That is, I have already told that it is the transfer function that is getting converted while you are converting or transforming an analog filter to digital filter. That is a transformation from continuous time to discrete time, that is from HS to HZ. Okay, so analog filters was first developed from since 1940, and digital filters are actually designed from the analog prototype. So analog prototype is actually the basis of IR filters, and that, so we'll have to learn more about this continuous time or analog filters, which we have already studied in our earlier sessions, like this Butterworth filter, Chebyshev 1 and 2 type filters, elliptical filters, right, that we all have studied. And what were the peculiarities for Butterworth? The frequency response, that is in pass band it's flat, whereas in also in stop band it's flat, whereas in Chebyshev 1 there are ripples in pass band, but in stop band it is flat, and in Chebyshev 2 just the reverse, whereas in elliptical filter there are ripples in both pass band and stop band. So we have already studied in detail about all these analog filters from which these digital filters are defined or designed. So now we will go to the present today's topic. So design of IR filters from analog filters. So digital filters perform the same filtering function as that of analog filter, except filtering is implemented on digital samples of the signal, that we know. Now these are the various steps that are involved in order to design an IAR digital filter from analog filter. So few steps that I have already said, that is, digital filter specification is first converted into analog filter specification. Then using analog frequencies, the transfer function or the system function HZ of the HS of the analog filter is found out. Later that system function of the analog filter, that is HS, is then converted into the system function of the digital filter, which is HZ. Okay, So it is that is how an analog filter is converted to digital filter. We are actually converting or transforming or mapping the system function of an analog filter to the system function of the equivalent digital filter. Okay, now these are the various methods used. Now for today we will learn the topic, that is, we will first see how an LER filter is designed by using approximation of derivatives technique. Now see, this particular technique I have explained a few words while we were dealing with the introduction part. I mean, I think it is in class 3, that is, I have described about all these methods of designing IR filter from digital filter, just a brief paragraph. So I think this also I have discussed briefly in class 3. So please, you can, if you want, you can go to class 3 to see the brief things of this particular method. But for your exam point of view, a more detailed version is required. So for your exam, you can study this one. Okay. So how to design an IR filter by using approximation of derivatives method. So in this method, an analog filter is converted into a digital filter by approximating the differential equation by an equivalent difference equation. Now the backward difference formula is substituted for the derivative dy by dt at time t equal to nt. This same sentence I have also said in class 3. Okay, so please refer to that. Thus dy by dt at time t equal to nt is given by this. This also I have explained in class 3, that is, you have one point, say y of nt, and another point y of nt minus t, and both of these are separated by a time period capital T. In this case, you will have to subtract these 2 points, that is a numerator, and then divided by their gap, capital T, that will be the denominator. On taking t as common, you will reach at this particular equation. This part I think I have discussed in class 3. Okay. Now Vrt is a sampling interval and y of n is equivalent to y of nt, the system function of an analog differentiator with an output dy by dt is hs, that is equal to s, and the digital system that corresponds the output y of n minus y of n minus 1 by t has a system function hz, which is given by 1 minus z raised to minus 1 by t. Now you are comparing these two, that is, the system function of analog filter is represented as hs, as already said before. Now it is again equivalent to represented by a small letter s, whereas the system function of a digital filter, that is hz, is represented by the formula 1 minus z minus 1 by t. Now you are equating these two. So how will be the equation like? S is equal to this one. S will be equal to 1 minus z raised to minus 1 by t, equation 2. Okay. Now you are going to find the second derivative, that is d square y by dt square. So that will be d by dt of dy by dt. So on simplifying, you can directly write this particular equation, and then the equation equivalent to this equation 3 in frequency domain is represented as this: s square is equal to 1 minus z raised to minus 1 by t the whole square. So this expression you can directly write this, and for s square you can directly write this particular equation. Now just compare the equations 2 and 4. So s is equal to 1 minus z raised to minus 1 by t. S means s raised to 1. Okay. Now what is equation 4? S square is equal to 1 minus z raised to minus 1 by t the whole square. That is, you are just squaring this equation 2. That is, LHS you are squaring and RHS you are squaring. So if it is like that, then what will be s raised to I? Ith term, s raised to I will be 1 minus z raised to minus 1 by t whole raised to I. Okay. See, that equation is written here. Okay. Now that is equation 5. Now as a result, the digital filter system function can be obtained by the method of approximation of derivatives as h of z is equal to h of as at s equal to 1 minus z raised to minus 1 by t. Here h of as is the system function of analog filter characterized by differential equation. Now we will see how the mapping is done. The outcome of mapping or transformation of Z plane from S plane are discussed below. That is how you are converting the system function or transfer function from analog system, that is from S plane, to the system function in digital system, that is in Z plane. That is a transformation or mapping from S plane to Z plane, or transformation from analog system to digital system. Now we can write equation 2, and another equivalent equation for equation 2 is Z equal to 1 minus 1 by 1 minus ST. Okay, now here you are going to substitute j omega in place of st, assuming it to be a complex one. So Z equal to 1 minus 1 by 1 minus j omega t. Now it will be like this. How this is obtained? You are just multiplying and multiplying both numerator and denominator with the 1 plus j omega t. Then you will reach this particular equation. That is this equation 1 by 1 minus j omega t. This one 1 plus j omega t divided by 1 plus j omega t. You are multiplying both the numerator and the denominator of this particular equation with the 1 plus j omega t. So that will simplify to 1 plus j omega t divided by 1 plus omega square t. This is omega. Okay, now splitting each one, that is you will get the first term as 1 by 1 plus omega square t, this one. Okay, then this one you are taking it separate, so it will be j omega t by 1 plus omega square t, this particular term. Okay, so this equation is obtained by multiplying both the numerator and denominator of this equation with the 1 plus j omega t. So you will reach at this particular equation as I shown. Then varying omega from minus infinity to plus infinity, the corresponding locus of points in Z plane will be a unit circle with radius half and center half. Let's see, this is how the mapping is done from S plane to Z plane. Okay, this is a Z plane, this is the S plane. So you are just our aim is to convert the system function of an analog filter to an equivalent system function of a digital filter. So first we have to do a mapping from S plane to Z plane. See, this is a left side of S plane, this is a right side of S plane. Now the left side of S plane actually corresponds to a unit circle. That is, it is mapped, that is left half of the S plane is actually mapped inside the unit circle. See, it is a circle of radius half and center half, whereas the right half of this S plane is mapped outside the unit circle, that is the outer circle. This is how the mapping is done. Left half of S plane is mapped inside the unit circle and the right half of S plane is mapped outside the unit circle. So as a result, this mapping since it represents circles, we will get a stable analog filter. That is, we have transformed a stable analog filter to a stable digital filter. Why? We are dealing with unit circles. However, the locations of poles and in the Z domain are confined to small frequencies. Since it is confined to small frequencies, this approximation of design method can be used only for transforming analog low pass filters and band filters having small frequencies, whereas a high pass filter or a band reject filter cannot be realized, or they cannot be used using this particular technique. Now, so here we have usually used the backward difference technique, right? Now let us see how the forward difference technique will apply in case of approximation of derivatives. For that, the only change is that in the equations that we have started, you are just replacing the minus sign with the plus sign. Okay, then the transformation formula will be of this form. So Z will be, from this equation, it will be 1 plus ST. That is, we are dealing with forward difference equations. Okay, now when dealing with the forward difference equations, let's just see how the mapping. When backward difference is done, the mapping was actually in the form of a circle. But whereas when we use forward difference, let us see how the mapping is this mapping while using forward difference is very worse. See, this situation is worse situation than when compared with the backward difference. Why? Because when s is equal to j omega, the mapping of these points in the s domain actually results in a straight line in the z domain. That is, when we are mapping from s plane to z plane, we are actually getting, instead of circles, we are getting some lines or straight lines. Hence, it is not possible to maintain the stability of filters. That is, it is not possible to convert a stable analog filter to a stable digital filter. So that type of mapping from stable form to stable form is not possible. So backward difference method is the most suitable one for converting or for mapping from S plane to Z plane, or for converting a stable analog filter to stable digital filter. This forward, why we are in mapping we are having only circles, whereas this forward difference method is not suitable. Why? Because when mapping is done from S plane to Z plane, we'll have to deal with straight lines, and so since straight lines are present, it is not possible to convert a stable analog filter to a stable digital filter. So that particular method is ruled out. We only take backward difference method. Okay. Now, the limitations of these two mapping methods discussed above is overcome by the substitution for derivatives. Now, we are now dealing with the nth term, or nth order difference is proposed for the derivative. So, here anyway you will have to learn this equation about dealing with the nth term. So, where a set of k are a set of parameters selected so as to optimize the approximation. Now the transformation from S plane to Z plane is then represented by this particular equation. These two equations you will have to study. This is a basis of the approximation of difference technique. Now by choosing proper values for a of k, the j axis can be mapped into unit circle, and the left half S plane can be mapped into points inside the unit circle in the Z plane, as I already said. So this is how approximation of derivatives method is used for mapping from S plane to Z plane, or for converting a stable analog filter to a stable digital filter. Now for your exam, sometimes if they ask a problem to solve, I have represented here just a sample problem, that is using backward difference, that is from for the derivatives. From that sentence itself, you will have to understand that you are asked to solve this problem using the approximation of derivatives technique. Okay, and convert the analog filter with system function. The system function they will give, that is h of s is equal to 1 by s square plus 16. H of s actually stands for what? From this you can say it is actually they are giving the system function of S plane, or the system function of the analog filter. Now you will have to convert this to the system function of digital filter. Okay, that will be Hz. You will have to find Hz. Okay. See, Hz you will have to find, that will be the answer. So you know the formula for conversion from S plane to Z plane, that is for conversion from analog filter to digital filter using approximation of derivative technique. This is the formula. Now you know Hz is equal to H of S at S equal to 1 minus Z raised to minus 1 by T. This is the S plane analog filter, this is the Z plane digital filter. Now in place of S, 1 by, here this is a question, 1 by s square plus 16. In place of s you will have to substitute this, so you will get this equation. Now expand. Now finally putting t is equal to 1 second, you will get the equivalent transfer function of the digital filter. That means you have now converted this analog filter to an equivalent digital filter using approximation of derivatives method. So that's all about this technique. In the next class we will learn about various other techniques like impulse invariance technique, bilinear transformation, etc. Okay, that's all for today. Thank you.